In this screencast, I'll talk about how to calculate confidence intervals for a population mean. But to proceed with this, you first have to accept the fact that this ratio is t-distributed. And if you don't know where that comes from, see my prior simulation on how the t-distribution arises from that ratio. But we'll proceed with the fact that that ratio is t-distributed. And t-distributions are actually a family of distributions which depend on the number of degrees of freedom. And the number of degrees of freedom is just the sample size minus 1. So here we'll use nu for the number of degrees of freedoms, n minus 1. And in this case, I've got a sample size of 2, or 1 degree of freedom for this curve right here. So I'll call it t subscript 1. And in this case, I've got a t-distribution with an infinite number of degrees of freedom. So in this case, it's as though you collected an infinite number of measurements for your sample. The number of degrees of freedom approach infinity, we come up with a normal distribution. So I'm showing two distributions, a normal distribution with an infinite number of degrees of freedom, and one with only 1 degree of freedom. And one thing to take away from this is the smaller your sample size, the smaller the number of degrees of freedom, the wider the tails are on either side. One thing that's important to recognize is the percentage of area that is to the right or to the left of a particular line. So I'm going to draw a line. I want to figure out for T1 with 1 degree of freedom, I want to figure out the percentage of area that's to the right of this line. Or we'll say, let's say I know I want a location in which 10% of the area is to the right of that line. And what I find is a value of T where that occurs is 3.078. And so what that means is 90% of the area is smaller than 3.078 for a t-distribution with 1 degree of freedom. And I could do the same thing for a t-distribution with an infinite number of degrees of freedom, or normal distribution. And what I find is I'm eyeballing this value, but this value is about 1.282 on the graph. So with an infinite number of degrees of freedom, 10% of the area is to the right of 1.282, and 90% of the area is to the left of 1.282. And one thing to take away from this is that when the number of degrees of freedom, or the sample size, approaches infinity, this cutoff approaches 1.282. When we calculate confidence intervals, we really want to know the fraction of time that we will get this ratio in this area. So what I'm calculating here is I've got a case in which 80% of the area is contained in the white, I've got 10% of the area in the red on the right side, and I've got 10% of the area in the red on the left. So if I were to do this, I would calculate values of t in which this occurs. So here I've got a value of t of 3.078, and here I've got a value of t of negative 3.078. And again, this particular curve is a t-distribution with 1 degree of freedom, or a sample size of 2. Typically, however, we never really calculate an 80% confidence interval. What's more common is either a 90% or a 95% confidence interval. So what I'm showing here is the same distribution, a t-distribution with 1 degree of freedom, in which I've got 95% of the area in white. And at this scale, you can't even see where the cutoff is. It's right around here at 12 or 13, positive or negative 12 or 13, somewhere in there. The only way to see that is if we zoom in on these regions. So let's zoom in on a region right around here. In this graph, I've done so. So I'm showing the right-hand tail where I've got 2.5% of the area in the right, and that just extends out to infinity out to the right is the area there. In this critical value of t right here, we'll use the notation. It's a t-distribution with 1 degree of freedom, with a value of 0.025, which means 2.5% of the area is to the right of this value. And I look that up in a table, or I use a computer to calculate it, and I come up with a value of 12.706. So for values of t less than 12.706, I encompass 97.5% of the area. So if I go back to my full scale, I've got 12.706 over here, and on the left side for values of t that are less than negative 12.706, I also have 2.5% of the area to the left of that mark, and 95% of the area in between the two. So because we have to accept that this ratio is equivalent to a t-distribution, we could say that the probability of this ratio, which is the sample mean minus the population mean divided by the sample standard deviation divided by the square root of n, we'll say that the probability of that being between negative 12.706 and 12.706 is equal to 95%. Another way to write this is that there's a 95% probability that that ratio is greater than negative 12.706 and less than 12.706. So if we accept that this ratio is t-distributed, in this case I've got n equals 2, a sample size of 2, that means that there's a 95% probability that this ratio is greater than negative 12.706 and less than positive 12.706. But remember, we don't ever get to know anything about the population mean itself. We're just trying to establish a range that it could be. And so to get at this, I'll perform a series of algebraic manipulations. So the first thing I'll do is multiply this expression by negative 1, and in doing so I have to change the direction of the inequalities. The next thing I'll do is multiply the whole expression by the sample standard deviation divided by the square root of 2. So that says now we know that the population mean has got to be between these two values. There's a 95% chance that it's between these two values, or maybe a way that's easier to interpret is if I rearranged it again slightly, there's a 95% probability that the true population mean is greater than the sample mean minus this value and less than the sample mean plus this value. Or equivalently, I could say the 95% confidence interval for a sample size of 2 is x bar, the sample mean, plus or minus 12.706 times the sample standard deviation divided by the square root of 2. Let's do something similar. Instead of a sample size of 2, let's calculate a 95% confidence interval for n equal to 30. So for n equal to 30, I've still got x over bar plus or minus. Now this is a smaller value. I get a value of 2.045 times the sample standard deviation divided by the square root of 30. In this value, 2.045, we'll call it the t-distribution with 29 degrees of freedom, and we want to know the probability of them being greater than 97.5%, or we could say the probability of them being less than 97.5%. So I look that up in my t-table or in my computer, and I find a value of 2.045 for this. Now I don't know why, but there's nothing special about n equals 30, but oftentimes in textbooks they'll say if n is equal to 30, you could assume that the distribution was normally distributed. So in essence what you're doing is a t-distribution with an infinite number of degrees of freedom. So in that case you would look up a value of 1.96. And I don't know why they do it, because unless the sample size is infinite, it's still considered a small sample, and I would never use 1.96 if I only had 29 degrees of freedom. The value it should be is 2.045. To demonstrate this graphically, I'm overlaying a normal distribution on top of a t-distribution with 29 degrees of freedom. In red are the actual tails that we should be using, and then the black vertical line is if it was normally distributed or there was 100 degrees of freedom. So to make it more clear, let's zoom in on this right tail, and in this instance we can see here is the normal distribution, and up in here is the t-distribution with 29 degrees of freedom. This is the value of 2.045 with 29 degrees of freedom, and this value here is 1.96, assuming we have an infinite number of degrees of freedom. And you'll see what happens if you use 1.96. You're actually making 95% confidence intervals that are slightly too small. So in general, I would just use a t-distribution regardless of the numbers of samples that you have, and you'll be correct and you don't need to make that approximation. Another interesting thing worth pointing out is as the number of degrees of freedom approaches infinity, this value, the critical value of t, approaches 1.96, but your n approaches infinity, which suggests that as you increase the sample size, your 95% confidence interval will approach the sample mean, and your 95% confidence intervals get smaller and smaller until eventually they reach 0, should you be able to collect an infinite number of samples. So the greater the sample size, the better handle you have on the true population mean, and the smaller your confidence interval.